Something arrived at the edge of our solar system in early July 2025. Not from another planet, not from the asteroid belt, from somewhere beyond the reach of our sun's gravity, from interstellar space itself, its designation, 3I Atlas. And when James Webb locked onto this visitor from the deep cosmos, what it revealed shattered every assumption about comets we thought we knew. This is not your typical solar system comet. This is a messenger from another star system, possibly 8 billion years old, older than Earth itself, older than our entire solar system. When Webb's near-infrared spectrograph instrument captured its first light from 3I Atlas on August 6th, 2025, the data that came back left astronomers staring at their screens in disbelief. If you value documented space discoveries like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. This script is researched and factual. Using sources from the arXiv preprint server repository, where Martin Cordner of NASA's Goddard Space Flight Center published the Webb telescope findings on August 25th, 2025, and the European Space Agency's Near-Earth Object Coordination Center tracking data published September 19th, 2025. These aren't mainstream media summaries. These are the raw scientific papers where astronomers first reported their shock at what Webb discovered. Now back to the information. July 1st, 2025, Rio Hurtado, Chile, the Atlas Telescope, Asteroid Terrestrial Impact Last Alert System, captures something moving against the background stars. Not unusual. Atlas finds space rocks every night, but this one is different. Its path traces a hyperbola, not an ellipse, not bound by the sun's gravity, coming from outside our solar system at 130,000 miles per hour, the fastest comet ever recorded. By July 2nd, 3 different observatories confirm what Atlas suspected. Canada-France-Hawaii Telescope on Mauna Kea, Lowell Discovery Telescope in Arizona, Deep Random Survey in Chile, all see the same thing, a faint coma developing around the nucleus, cometary activity. The Minor Planet Center announces the discovery, 3I Atlas, the third interstellar object ever confirmed. But here's where the story gets strange. Most comets start out gassing when they reach about 3 to 4 astronomical units from the sun. 3I Atlas began its coma formation at over 5 astronomical units out. Early. Too early for a typical comet. The Hubble Space Telescope captured its first images on July 21st, 2025. Distance from Earth, 277 million miles. What Hubble revealed stopped astronomers cold. A teardrop-shaped dust cocoon streaming from the nucleus. But the size estimates were all wrong. The nucleus diameter, somewhere between 440 meters and 5.6 kilometers. The most likely size, less than 1 kilometer across. For something generating that much visible activity at that distance, it should be bigger, much bigger. Then came the call every astronomer had been waiting for. James Webb Space Telescope. August 6th, 2025, target acquired, NIR-spec instrument online. Spectral range, 0.6 to 5.3 micrometers. What Webb saw in those infrared wavelengths had never been recorded before in any comet anywhere. Carbon dioxide dominated the entire coma. Not water, not the typical mix astronomers expect. Pure, overwhelming carbon dioxide outgassing at rates that defied explanation. Webb's data revealed the carbon dioxide to water ratio, 8 to 1, the highest ever measured in any comet, 6 standard deviations above normal values for long-period comets. In statistical terms, this shouldn't exist. Yet there it was, blazing in infrared light, impossible to deny. Webb also detected water ice, water vapor, carbon monoxide at normal ratios, and carbonyl sulfide, a compound that smells like rotten eggs when it sublimates. The production rates Webb measured tell the real story. 129 kilograms of carbon dioxide per second streaming from the nucleus, 6.6 kilograms of water per second, 14 kilograms of carbon monoxide per second, 0.43 kilograms of carbonyl sulfide per second. These aren't estimates. These are direct measurements from the most powerful infrared telescope ever built. NASA's SphereX Observatory confirmed Webb's findings between August 7th and August 15th, 2025. Multiple telescopes, independent observations, same result. 3. I-Atlas is unlike any comet we've ever encountered. Where did this thing come from? The trajectory analysis provides disturbing answers. When astronomers trace 3I Atlas backward through space, accounting for gravitational perturbations from every star within 30 light years, the path leads toward the galactic core, the center of the Milky Way, 30,000 light years away. If their calculations are correct, 3I Atlas has been traveling for 8 billion years. 8 billion, that makes it older than Earth. older than our solar system by 3 billion years, the oldest object humans have ever observed up close. Think about what that means. This comet formed when the Milky Way was young, when our solar system didn't exist, when the materials that would become Earth were still scattered in interstellar clouds. 3I Atlas has witnessed the birth of countless stars, survived close encounters with stellar remnants, gained velocity through gravitational slingshots around objects we can't even imagine, all while preserving its original composition locked in ice, waiting for the day it would enter our solar system and reveal its secrets to human science. The carbon dioxide dominance isn't random. Webb's spectroscopic analysis suggests two possible origins. First, 3. I-Atlas contains ices exposed to radiation levels far exceeding anything solar system comets have experienced. Billion-year bombardment by cosmic rays and stellar radiation, slowly transforming the surface chemistry. Second, 3. I-Atlas formed at the carbon dioxide ice line in its parent protoplanetary disk, the precise distance where carbon dioxide transitions from gas to solid ice around a young star, a formation zone that produces comets with exactly the chemistry Webb observed. But there's a third possibility that makes astronomers nervous. The low water vapor readings might indicate something is preventing heat from penetrating deep into the nucleus. Some kind of internal structure or composition that suppresses water sublimation while allowing carbon dioxide to outgas freely. We've never seen this before. We don't understand the mechanism. We just know it's happening. If you value documented space discoveries like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. This research comes directly from the preprint archives, where working scientists publish their findings before peer review, giving us the most current data available. Now back to the information. 3I Atlas continues accelerating toward perihelion, its closest approach to the Sun. October 29th, 2025, distance 1.36 astronomical units, just inside Mars, a orbit. But this isn't a typical comet flyby. Mars will have front row seats. European Space Agency's Mars Express and ExoMars Trace Gas Orbiter are positioned to capture 3I Atlas during its closest approach to Mars on October 3rd. Distance 30 million kilometers, closer to Mars than it will ever come to Earth. The Mars orbiters will attempt high-resolution imaging using the high-resolution stereo camera and color and stereo surface imaging system. Multiple spacecraft, multiple instruments, all focused on an object that won't pass this way again for billions of years, if ever. ESA's Near-Earth Object Coordination Center has calculated trajectory corrections, accurate enough for Webb to track 3I Atlas through its tiny field of view. Precision astronomy on an interstellar scale. Ground-based telescopes continue monitoring as 3I Atlas develops its tail. Gemini South telescope captured tail growth images on August 27, 2025. The International Gemini Observatory team, led by research scientist Bryce Bolin from Eureka Scientific, documented particles changing composition as the comet heats up. The tail isn't just dust. It's a chemical evolution happening in real time as billion-year-old ices finally encounter stellar heat. The Nordic Optical Telescope confirmed cometary activity on July 2nd. David Jewett and Jane Liu, the team that discovered the first Kuiper Belt object, verified 3. I-Atlas was clearly active with diffuse coma structure. Tidy Observatory's 2-meter twin telescope found the same activity patterns. Multiple independent confirmations, no mistakes. No wishful thinking, pure observational science. But the strangest discovery came from TESS, the Transiting Exoplanet Survey Satellite. TESS wasn't looking for comets. It was monitoring stars for planetary transits. But TESS caught 3I Atlas in its field of view and recorded something unprecedented. The comet was already outgassing months before discovery. TESS data from May shows clear cometary activity when 3I Atlas was still beyond 5 astronomical units from the Sun. This violates everything we know about comet activation distances. The Very Large Telescope detected cyanide gas and atomic nickel vapor in 3I Atlas's coma at concentrations matching solar system comets, familiar chemistry mixed with the alien. The Zwicky Transient Facility found precovery images extending back to May 21st, 2025, multiple observatories independently documenting an object that shouldn't behave the way it does, coming from somewhere it shouldn't come from, displaying chemistry that shouldn't exist. Tony Santana-Ross published findings in August 2025, showing 3I Atlas's coma became redder throughout July as cometary activity increased. Color changes indicate surface composition evolution. Material that's been frozen for 8 billion years finally sublimating. Ancient chemistry meeting modern stellar radiation. The color shift matches predictions for dust particles with high carbon content, exactly what you'd expect from a carbon dioxide-dominated outgassing event. The numbers don't lie. 3I Atlas spans up to 5.6 kilometers across, but could be as small as 440 meters. The uncertainty comes from its unusual reflectivity. Most comets reflect about 4% of incoming sunlight. 3I Atlas reflects enough light to fool size calculations. Its surface is brighter than expected, possibly because billion-year cosmic ray exposure created unusual ice crystal structures, possibly because it contains materials we've never encountered before. The velocity tells its own story, 130,000 miles per hour relative to the Sun, hyperbolic excess velocity indicating billion-year acceleration through gravitational encounters with stellar objects. When 3I Atlas leaves our solar system, it will be moving even faster. Our Sun's gravity will add another kick, sending it deeper into interstellar space at speeds that will carry it to other star systems within cosmic eye blinks. Webb's follow-up observations are scheduled for December 2025 days after 3I Atlas emerges from solar conjunction. When the comet reappears from behind the Sun, it will be outgassing at maximum rates. Perihelion passage changes everything: surface chemistry, internal heat distribution, sublimation patterns. The December observations might reveal completely different spectral signatures, as billion-year-old ices reach temperatures they haven't experienced since 3I Atlas formed around its parent star. Hubble will continue monitoring through November with ultraviolet spectroscopy to determine sulfur-to-oxygen ratios in the gas emissions. UV observations reveal atomic transitions invisible to other wavelengths, element abundances that tell formation stories. Stellar nucleosynthesis signatures from the parent system, where 3I Atlas originated, chemistry lessons from across the galaxy. The implications cascade through astronomy. If 3I Atlas represents typical interstellar comet chemistry, then our models of planetary system formation need revision. If carbon dioxide-rich comets are common around other stars, then we've been studying an unrepresentative sample for decades. Every comet in our solar system formed under the same stellar conditions. 3I Atlas formed around a different star, under different radiation environments, in a different stellar neighborhood, 8 billion years ago. This is comparative planetology on an interstellar scale. Webb's data from 3I Atlas provides our first detailed chemical analysis of material from another planetary system. The carbon dioxide to water ratio suggests formation conditions, unlike anything in our solar nebula, either higher radiation levels that preferentially destroyed water ice, or formation at specific temperature zones where carbon dioxide dominated ice chemistry. The age estimates create their own problems. If 3I Atlas is truly 8 billion years old, it predates most of the Milky Way's star formation. It formed when the galaxy was younger, metal-poor, dominated by different stellar populations. Its parent system might have contained elements and ratios completely unlike the solar composition. We're not just studying an alien comet, we're studying fossil chemistry from an earlier epoch of galactic evolution. 3I Atlas will pass closest to Earth at 1.8 astronomical units on January 15th, 2026, still too distant for detailed surface observations, but close enough for continued spectroscopic monitoring as it develops maximum cometary activity. Then it disappears forever. Back into interstellar space, back to wandering between stars for billion-year intervals until random chance brings it into another planetary system. Unless we intercept it first, proposals exist for rapid flyby missions, spacecraft designed to launch on short notice when interstellar objects are detected. Flyby velocities would exceed anything previously attempted. Engineering challenges that push propulsion technology to limits. But the scientific return would revolutionize our understanding of other star systems. Direct sampling of alien planetary system material. Chemistry analysis impossible from Earth-based telescopes. The window is closing. Every day. 3I Atlas moves deeper into the inner solar system, heating up, losing mass, changing composition. The pristine 8 billion-year-old surface chemistry is sublimating away. By the time it reaches perihelion, the ancient ices will be gone, replaced by subsurface material that might tell different stories. We're watching fossil chemistry from another era of the galaxy evaporate in real time. Webb's detection capabilities extend far beyond 3I Atlas. The telescope can detect similar objects at distances where ground-based surveys miss them, fainter comets, more distant approaches, objects that pass through the outer solar system without developing visible comas. The era of routine interstellar visitor detection has begun. 3I Atlas won't be the last. It might not even be the most unusual. Statistical models suggest interstellar objects are the most common large bodies in the Milky Way. billions of rogue comets and asteroids ejected from planetary systems during formation, wandering between stars, occasionally passing through our solar system where we can study them. Chris Lintott from Oxford University estimates there's almost always at least one interstellar visitor within our solar system boundaries. We just haven't developed the technology to find them systematically. The Vera C. Rubin Observatory will change that equation. Starting science operations in 2025, Rubin will survey the entire visible sky every 3 nights. Automated detection algorithms designed to spot moving objects. Interstellar visitors will be identified within hours of entering observable range, multiple objects per year. Enough data to understand interstellar comet populations statistically, enough objects to trace back to parent systems and determine galactic distribution patterns. But 3, I-Atlas remains unique. The carbon dioxide chemistry, the extreme age, the probable galactic core origin, the perfect timing that brought it within range of humanity's most powerful telescopes, just as we developed the technology to decode its secrets. Billion-year journey through interstellar space, 8 billion years of cosmic evolution, all leading to August 6th, 2025, when Webb's instruments locked onto target and captured infrared light from the oldest object humans have ever studied. The data continues streaming in. Webb's NIR-spec observations contain spectral lines that haven't been fully analyzed, isotope ratios that might reveal stellar nucleosynthesis patterns from the parent system, carbon-13 to carbon-12 ratios partially obscured by dust but detectable in future processing, heavy water signatures, molecular species that exist only under specific radiation environments, chemistry textbooks written in light from an object older than Earth. 3, I-Atlas carries more than just ancient ice. It carries information about stellar system formation 8 billion years ago, about radiation environments in different galactic neighborhoods, about planetary system chemistry under conditions that no longer exist, about cosmic evolution on scales we've never directly observed. We're not just studying a comet, we're studying deep time, geological timescales written in space ice, archaeology on a galactic scale. The trajectory analysis reveals 3 I-Atlas's future as clearly as its past. After perihelion passage, it will swing around the sun and head back toward interstellar space. Velocity, approximately 40 kilometers per second relative to the solar system. Direction, toward the constellation Lynx. Destination, other star systems, other planetary neighborhoods, other opportunities for discovery by alien astronomers who might wonder where this ancient wanderer originated. In 40,000 years, 3 I-Atlas will pass within 2 light-years of the star system, Wolf 359, a red dwarf star with unknown planetary companions. If Wolf 359 hosts technological civilizations, they'll detect 3 I-Atlas approaching their system just as we detected it approaching ours. They'll point their most powerful telescopes at the visitor, they'll analyze its spectral signatures, they'll find carbon dioxide chemistry and wonder about its origins. They might trace its trajectory backward through space and realize 3 I-Atlas came from the direction of our solar system. They might wonder if the 3rd planet from the yellow star harbored life when 3 I-Atlas passed through. They might find isotope signatures in its ice that match their databases of stellar composition from our galactic neighborhood. Interstellar archaeology. Messages written in comet chemistry. Information transfer across cosmic distances through the patient migration of frozen messengers. But first, 3. I-Atlas has to survive its encounter with our sun. Perihelion passage subjects comets to extreme thermal stress. Surface temperatures reaching hundreds of degrees, internal pressure from rapid sublimation, structural failure, fragmentation, complete disintegration. Many comets don't survive their first close solar approach. 3. I-Atlas has traveled 8 billion years to reach this moment. Whether it survives depends on internal structure we can't directly observe. Webb's December observations will answer that question. If 3 I-Atlas emerges from perihelion intact, it will provide unprecedented data about 8 billion-year-old ice composition under extreme heating conditions. If it fragments, the debris field will reveal internal structure and allow analysis of subsurface material never exposed to space weathering. Either outcome advances our understanding of interstellar object composition and evolution. The research papers continue appearing on ARSIF. Martin Cordner's team from NASA Goddard published the initial Webb spectroscopy results. Colin Wilson from ESA's Near-Earth Object Coordination Center contributed trajectory analysis for Mars orbiter observations. David Jewett from UCLA led the Hubble imaging campaign. Bryce Boland from Eureka Scientific coordinated ground-based telescope observations. International collaboration on an unprecedented scale. Every major observatory contributing data, every available instrument pointed at the same target. This is how science works when presented with something genuinely unprecedented. Not gradual hypothesis testing, not incremental progress. Revolutionary discovery that demands immediate attention from the entire astronomical community. 3. I-Atlas forced astronomers to mobilize resources, coordinate observations, and share data in real time. The discovery timeline measured in days and weeks, rather than the usual years and decades of careful study. The spectral analysis techniques pushed Webb's capabilities to limits. Nirospec observations at the edge of sensitivity. Signal processing that extracted molecular signatures from noise levels that would defeat lesser instruments. Calibration procedures developed specifically for fast-moving targets with unusual spectra. Technical achievements that advance infrared astronomy beyond 3I Atlas applications. But the deeper mystery remains unsolved. Why carbon dioxide? Why such extreme ratios? Why formation chemistry unlike anything in our solar system? The answers require understanding stellar environments 8 billion years ago, galactic chemical evolution, interstellar radiation fields, planetary system formation under conditions we can model but never directly observe. 3I Atlas might represent normal interstellar comet chemistry. Our solar system comets might be the unusual ones, formed in a peculiar stellar environment that produced water-rich ice chemistry. We've been studying the exception, assuming it represented the rule. 3I Atlas suggests we've been wrong about fundamental assumptions regarding comet formation throughout the galaxy. Or 3I Atlas might be genuinely unique. A 1 in a billion object with formation history unlike typical interstellar comets. Chance encounter with radiation sources that modified its surface chemistry. Collision with another interstellar object that mixed compositions. Internal heating from radioactive decay that drove unusual sublimation patterns. The sample size of detailed interstellar comet observations remains exactly 1. The scientific papers acknowledge these uncertainties. Careful language about preliminary results. Calls for additional observations. Recognition that single object studies can't support broad conclusions about interstellar comet populations. But the data stands regardless of interpretation. 8-to-1 carbon dioxide to water ratios. Production rates measured in hundreds of kilograms per second. Spectral signatures unlike any solar system object. Webb's second observations in December will either confirm or modify these findings. Extended spectral coverage, different solar heating conditions, possible detection of additional molecular species as deeper ice layers sublime. The December data might resolve isotope ratio questions, partially obscured in the August observations. Carbon isotope signatures from the parent stellar system. Oxygen isotope patterns that reveal formation temperature conditions. Meanwhile, 3I Atlas continues its hyperbolic trajectory toward perihelion, heating up, outgassing accelerating, tail development visible in ground-based telescopes, chemical evolution happening in real time as 8 billion-year-old ice encounters stellar radiation for the first time since formation. We're watching fossilized chemistry from another epoch of galactic evolution return to life under the influence of our sun. The October Mars observations will provide different perspective angles. Multiple spacecraft, different instrument suites, observations impossible from Earth because Mars will be positioned on the opposite side of 3I Atlas during closest approach. Stereo imaging that might resolve nucleus rotation and surface features, composition gradients across the coma that indicate subsurface chemistry variations. Mars reconnaissance. Orbiter joins the observation campaign with its high-rise camera designed for surface imaging, but capable of astronomical observations. The Curiosity and Perseverance rovers will attempt photography if 3I Atlas becomes bright enough for surface observations. Multiple NASA missions coordinated for the same target. Unprecedented multi-platform astronomy focused on a single interstellar object. The coordination challenges are immense. Spacecraft designed for different missions. Instruments optimized for planetary rather than astronomical observations. Timing requirements that demand precise orbital positioning. Communication delays between Mars and Earth that complicate real-time observation coordination. Engineering problems solved specifically for 3I Atlas observations. But the scientific justification is overwhelming. This is the closest approach of any interstellar object to Mars in recorded history. The next similar opportunity might not occur for thousands of years. The Mars observation geometry provides angles impossible from Earth-based telescopes, three-dimensional coma structure, nucleus rotation measurements, surface feature detection at resolution limits. The data integration problems are equally complex. Different instruments, different calibration standards, different data formats, different analysis software, results that must be combined to create comprehensive models of 3I Atlas composition and behavior, international data sharing agreements, standardized processing procedures, quality control standards for unprecedented observation types. Yet the results justify every effort. we're studying 8 billion years of cosmic evolution preserved in ice, chemistry from an earlier epoch of galactic development, formation conditions around stars that died before our solar system existed, information transfer across space and time through the patient migration of frozen archives. 3, I-Atlas represents the oldest known object in our cosmic neighborhood, older than meteorites, older than the oldest Earth rocks, older than the oldest lunar samples. 8 billion years of continuous existence in the deep freeze of interstellar space, no atmospheric weathering, no geological processes, no biological contamination. Pure preservation of ancient chemistry, waiting 8 billion years to be discovered by human science. The implications extend beyond astronomy. Astrobiology considers 3I Atlas, a potential carrier of organic compounds from other star systems. Panspermia. Hypotheses suggest interstellar objects might transfer life between planetary systems, chemical precursors to biological processes, complex organic molecules that survive interstellar radiation, seeds of life distributed throughout the galaxy by wandering comets. Webb's spectral analysis will search for organic signatures in 3I Atlas's coma, carbon compounds beyond simple carbon dioxide and carbon monoxide, methane, formaldehyde, hydrogen cyanide, amino acid precursors, molecular species that bridge the gap between simple chemistry and biological complexity. The sensitivity limits push detection capabilities to theoretical boundaries, but organic compound detection faces contamination problems. Solar system comets contain organic molecules formed in our stellar nebula. Distinguishing local from alien organic chemistry requires isotope analysis beyond current capabilities. Carbon-13 ratios, nitrogen-15 signatures, oxygen-18 abundances. Isotope patterns that fingerprint stellar nucleosynthesis from the parent system. The biosignature search remains speculative. No confirmed detection of biological compounds in any interstellar object. No established protocols for distinguishing biological from abiological organic chemistry in comet spectra. No consensus on what constitutes convincing evidence for life transfer between star systems. But the search continues because the implications would revolutionize our understanding of life's cosmic distribution. 3. I-Atlas also carries implications for planetary defense. Interstellar objects approach from arbitrary directions at high velocities. Current detection systems assume objects originate within the solar system and follow predictable orbits. Interstellar visitors appear suddenly with minimal warning time. Impact probabilities remain low, but consequences could be catastrophic. The Atlas survey system that discovered 3I Atlas was designed for solar system asteroid detection. Interstellar object discovery was accidental. Purpose-built interstellar visitor detection systems would require different survey strategies. All-sky monitoring. Extremely sensitive instruments. Automated analysis systems capable of distinguishing interstellar from solar system trajectories within hours of detection. But 3. I-Atlas poses no threat to Earth. Closest approach distance, 1.8 astronomical units, no possibility of impact. No gravitational perturbation of Earth's orbit, no debris hazard from tail material, pure scientific opportunity without planetary defense concerns, the ideal interstellar visitor for detailed study without risk assessment complications. The observation window continues narrowing. Every day. 3. I-Atlas moves closer to solar conjunction where it becomes unobservable from Earth. The November-December gap, when it disappears behind the Sun as seen from our planet. Mars observations fill part of this gap, but large data gaps are inevitable. Critical perihelion passage occurs during conjunction when Earth-based telescopes can't observe. Space-based telescopes continue observations during conjunction. Webb, Hubble, Solar, and Heliospheric Observatory, spacecraft positioned at different angles around the Sun. Partial coverage during the most crucial phase of 3I Atlas's solar system passage. The period when 8 billion-year-old ice encounters maximum heating and reveals its deepest chemical secrets. The December reappearance will show whether 3I Atlas survived perihelion passage intact. Fragmented objects displayed different spectral signatures. Debris fields with separate components. Chemical segregation, where different ice types sublimate at different rates. Internal structure revelations, impossible during approach phase observations. Survived objects show evolved chemistry. Surface layers stripped away. Subsurface material exposed. Different isotope ratios from material that hadn't been space-weathered for 8 billion years. Fresh surfaces that reveal formation chemistry unmodified by cosmic ray exposure. Archaeological layers in space, ice recording different epochs of cosmic evolution. The follow-up observations extend through spring 2026, Hubble ultraviolet spectroscopy, Webb extended infrared coverage. Ground-based telescopes tracking 3I Atlas as it recedes from the inner solar system. Gradually fading signals, weakening spectral lines, the slow farewell to humanity's most ancient visitor. By summer 2026, 3. I-Atlas will be too faint for detailed spectroscopic observations. The data collection window closes forever. Analysis continues for years using archived observations, but no new data, no second chances, no return visits. The 8 billion year journey through space ends with a few months of human observation before departure back to interstellar darkness. The legacy data archive will support decades of research, spectral libraries, composition models, formation theory tests, comparative planetology studies using the only detailed chemical analysis of material from another star system, PhD dissertations, postdoctoral research projects, theoretical papers, exploring implications for galactic chemical evolution. But the immediate science focuses on extraction of maximum information from existing observations, isotope ratio analysis, pushing Webb's sensitivity limits, molecular species identification in noisy spectra, production rate calculations from multi-epoch observations, nucleus size constraints from photometry and thermal modeling. Every available analytical technique applied to the most ancient object humans have studied. The international research collaboration continues expanding. European Southern Observatory, Japanese Space Agency, Indian Astronomical Institutes, Chinese Academy of Sciences, Global Coordination for Data Sharing and Analysis, the first truly international study of an interstellar object, scientific diplomacy through shared exploration of cosmic visitors. 3I Atlas has already transformed interstellar object science from speculation to observational astronomy. Detailed chemical composition data, accurate trajectory measurements, multi-wavelength observations across electromagnetic spectrum, the foundation for statistical studies when future interstellar visitors are detected, template observations for comparative analysis. The next interstellar visitor might arrive next year or next decade. Random timing based on galactic dynamics beyond human prediction. But when it arrives, astronomers will be prepared. Observation protocols developed for 3I Atlas, instrument configurations optimized for fast-moving targets, data analysis procedures tested and refined, international coordination mechanisms established and proven. 3I Atlas also demonstrates the critical importance of rapid response astronomy. Objects with short observational windows require immediate resource allocation, flexible telescope scheduling, priority target designation, coordinated multi-facility campaigns, administrative procedures that support science discovery rather than hindering it through bureaucracy. The Webb telescope observations represent the technical pinnacle of current infrared astronomy, sensitivity levels that detect molecular signatures from objects millions of kilometers away, spectral resolution that separates closely spaced emission lines, calibration accuracy that enables quantitative chemical analysis, the technological foundation for interstellar object studies throughout the next decade. But Webb's capabilities will be exceeded by next-generation instruments. The extremely large telescope under construction will provide higher spatial resolution. The proposed Origins Space Telescope will extend infrared sensitivity to longer wavelengths. Future missions specifically designed for interstellar object studies. Technical evolution that builds on 3I Atlas discoveries. The theoretical implications continue expanding through academic literature. Stellar formation models, galactic chemical evolution theories, planetary system architecture around different stellar types, interstellar medium composition in different galactic environments, research directions that emerge directly from Webb's observations of ancient ice. 3. I-Atlas has also inspired public interest in astronomy at levels rarely seen for scientific discoveries. Social media coverage, news articles, documentary productions, educational programs, public fascination with visitors from other star systems, science communication opportunities that explain complex astrophysics through compelling storytelling about cosmic wanderers. The educational impact extends through university curricula, graduate courses on interstellar objects, research methods for fast-moving targets, data analysis techniques for weak spectral signals, career preparation for astronomy students who will study future interstellar visitors throughout their professional lives. 3I Atlas represents a watershed moment in human cosmic exploration, not just discovering that interstellar objects exist, but developing the capability to study their detailed composition and origin. The transition from detection astronomy to analytical chemistry of alien materials, scientific advancement that transforms speculation into quantitative measurement. As 3, I-Atlas approaches perihelion. Every day brings new data, changing production rates, evolving spectral signatures, chemical reactions in real time as billion-year-old ice encounters stellar heating. We're watching 8 billion years of cosmic preservation end through sublimation and dispersal into interplanetary space. But the scientific legacy begins as the physical object disappears. Data archived for future analysis, techniques developed for future applications, international collaboration tested and proven, theoretical frameworks established for understanding interstellar comet populations, the foundation for an entirely new field of astronomical research. This is how science advances through revolutionary discovery, not gradual progress building on previous knowledge, but sudden encounter with phenomena that require completely new analytical approaches. 3I Atlas forced development of interstellar visitor science years ahead of predicted schedules. Crisis-driven innovation that produces lasting advances. The final observations, scheduled for spring 2026, will close the 3I Atlas chapter of human cosmic exploration. But the story continues with future interstellar visitors, better prepared observations, more advanced instruments, deeper understanding of galactic comet populations, statistical studies that place 3I Atlas in context with other ancient wanderers. Yet 3I Atlas will remain unique as humanity's first detailed encounter with fossilized chemistry from another epoch of cosmic evolution. 8 billion years of deep time preserved in ice and revealed through the patient application of 21st century astronomical technology. Archaeological discovery on the largest possible scale, written in light from an object older than Earth itself. On January 31st, 2026, at approximately 1400 Universal Time Xiao, 3I Atlas will cross back beyond the orbit of Mars, heading outward toward interstellar space. The last detailed observations will have been completed months earlier. The ancient wanderer returns to darkness, carrying with it the secrets we couldn't extract in our brief encounter. But in the archived data streams, in the peer-reviewed papers, in the theoretical models developed to explain its impossible chemistry, 3I Atlas leaves behind humanity's first scientific portrait of deep cosmic time. 8 billion years of galactic evolution, captured in infrared spectroscopy and preserved forever in human knowledge.